be from Moshe Voloshin from Broadcom. He's a system architect in Data Center Solutions Group Division, DCSG at Broadcom. Moshe spearheaded the system architecture development of Rocky and congestion control in Broadcom Ethernet NICs, involved in definition of product architecture, modeling, and system simulations. Previously, Moshe was director, manager of the ASIC hardware engineer at CIS. Where he developed and managed the development of network processing unit, the NPU, QoS, fabric ASICs, and products such as GSR and CRS. So today's talk, mostly he will be focusing on the benchmarking aspects of HPC and ML communication. So let's give a big hand in welcoming Moshe.
Hear me well? Yeah, looks like it's good. Yeah.
Okay.
All right. You have to. Great. Thank you, Dr. Parna. I'm going to talk about HPC benchmarking. What are the different classes of benchmarking and how they can be used? What's the usefulness of them? And also raise the question whether there is room for an intermediate class of new benchmarks. So I'll start with why we need benchmarking. The focus is communication, benchmarking for communication. Talk about the different classes and cover some samples of the existing benchmarks in the different classes, such as micro benchmarks, as well as HPC benchmarks and machine learning benchmarks. Talk about aspects of benchmarks for congestion control in the network, performance monitoring tool, the need for automation and analysis when running a large search of benchmark for evaluation, and talk about the possible gaps in benchmarking and what we as a community can do about it. Yeah. So there are different aspects of why benchmarks are useful. Usually the benchmark intend to test the complete system, which include different machines, CPU, memory, I/O, file systems, operating systems, the different communication library or MPI libraries, and so on. This talk, however, will focus mainly on the communication aspects of the benchmark. And the reason where, the place where this is important is, of course, when the application is running not on just one system, but it's distributed and possibly could scale to hundreds or even thousands of nodes. And at this stage, then the communication plays a very important part of the usefulness and performance of the overall system. In HPC and machine learning, there are different types of communication. Simple communication, such as point-to-point send and receive, or put and get. But there is also the more complicated operation called collective that involve multiple nodes or group of nodes. Sometimes the communication is happening on the network where one group of nodes, which is a subset of the systems, is communicating. Sometimes it could be multiple such systems that share the same network to carry out the communication. And there are different interactions that could happen within the group and between groups and so on when everything's traversed the same pieces of the network, of the infrastructure. Communication patterns of different processes can be represented by logical topology. There is, of course, the physical topology or the network topology of how different machines connect to the network through what kind of network elements, switches, and so on. But there is also an important piece of it when it comes to collective, and this is how the different nodes that are part of the group that communicate together are organized in delivering the data to each other. And this is called a logical topology, and it could be that nodes are communicating in a ring fashion, basically by neighborhood exchanging data only with the nearest neighbors. It could be a binary cube or tree and so on. There are different topologies and they come into play in collectives. Selection of the logical topologies is usually done by MPI library or whatever is the HPC library in use. And it usually depends on the number of ranks that participate in the operation. This is the number of ranks that need to exchange data, as well as the message size. Usually, there are all kinds of tuning and optimization done over the years to be able to automatically select the correct topology or the most appropriate topology for the communication type. All of these things, the selection of algorithms, what kind of algorithms exist, and so on, have a significant impact on performance. And benchmarks can give us a way to evaluate how all the pieces comes together in performing and carrying out the operation. So there are two main classes of benchmarks, and there is somewhat, on the next slide I'll talk about an intermediate class. There is the first one is the lowest level, is the micro benchmarks, where micro benchmarks usually carry out a single operation at a time. It doesn't try to do anything more than a single operation. So you could test communication between two nodes, maybe a collective between multiple nodes, but it usually carry out one operation and report some metric about the operation. And the metric could be bandwidth or completion time, sometimes called latency. The main functionality that this kind of benchmark covers is MPI layer, of course, including the collective algorithm and the automatic selection of them. The API, which is what comes in between the MPI library and the provider software and firmware. These are, for example, OFA verbs in the case of RDMA, OFI or UCX, and of course the provider software, and the actual hardware that carry out do the offload in case of ROCI and RDMA. As well as the network elements and the congestion control and how they interact together. So these are this is the list of functionality that are covered by the micro benchmark. The higher level of benchmark is really application benchmark, where we have a complete code that aim at doing some simulation or some training or some other type of communication that computation that is distributed. And in this type of benchmarks, what's happened throughout the benchmark is both computation and communication with various patterns of interactions. The metrics is usually completion time and also scaling, how the application performance scale with the number of nodes and the number of processes per node. The functionality components under evaluation in this case is much broader. Everything that I mentioned before, but on top of that, it could include the CPUs or GPUs, memory, I/O, operating system, and so on. So the scope of these benchmarks is much larger. It gives the user that want to run this kind of application a good indication of how the whole system, everything comes together and how it's going to perform. There is also a third class, I would say, of benchmarks. It's kind of a intermediate level between the low-level micro benchmark and the application benchmark. And these kind of benchmarks try to be more generic, but they still focus on some type of communication. So some examples of those is the HPL, HPCC, which I'm going to talk a little bit more about later. They usually combine several types of one or more types of computation and with the necessary communication that come with them. Another type of benchmark that is in this area is focused on the network effect and the congestion control. This is a benchmark called GPC-Net. It aims at evaluating the effectiveness of the network as well as the congestion control system. And it measures the impact of the network under load. So it could, for example, take some operation, measure how they perform with no load in the network, and then compare that with how they perform when there is significant load in the network. The way that GPC-Net is built is that it's really aimed at testing large systems, and I'm going to talk a little bit about that. So out of these three classes, the low level, the intermediate level, and application level, some questions may be asked, is there a need for other mid-level benchmarks and how they can be useful? They could be, for example, more generic than a specific application benchmark, but still richer than a micro benchmark. Richer could be, they're not necessarily going to do one type of operation or one type of collective. They're going to try to do something a little bit more than that. And the possible scope for this kind of things is, for example, some mix of collective that relevant for a category. For example, if it's storage or HPC or deep learning, what's relevant to this kind of computation application. But it could be creating the relevant pattern of communication, the combination of this collective without necessarily carrying out all the computation. So it's really focused on the communication part, and it's mimicking what kind of transactions and relationship between transactions happen in each of the category. This can allow a much faster iteration and evaluation without carrying out the whole sequence of operation that will happen in an application. And of course, combine a collective operation and as well as a background load, similar to what GPC done, but maybe in a smaller network. That you could take a single switch with few nodes and still get the learning that is required to understand how the system will operate under congestion control. So I will, in this part of the presentation, I'm going to go a little bit about, talk about a little bit about each of the classes, giving some examples of the type of benchmarks under each class. So we'll start with the micro benchmark. Again, the micro benchmark are benchmarks that intend to test a particular type of operation. It could be send or RDMA write or RDMA read. It could be a little bit more complex, such as communication that the MPI library would implement, collective. So at the lowest level, there is the Linux RDMA perf test. This is a small set of tests that test point-to-point communication basically between two nodes. They carry the basic operation of RDMA, and they do not use MPI library. They really use just the native verbs interface to the provider software and hardware, and test these components, really, the native verb interface and the provider software. It's good to test the functionality, that everything's worked right at that level, and you could test bandwidth and latency and simple things like that. A little bit above that, still micro benchmark, there is the unknown OSU benchmark, or Intel MPI benchmark, as well as the nickel and RICL tests. These use the communication, they use the MPI library or some communication library in case of nickel to carry out a more advanced operation than just the point-to-point communication. Of course, they include the point-to-point communication, but they also test particular collectives like all reduce and all-to-all, broadcast, and so on. They do that from the library point of view, where they put together the whole infrastructure that require on the number of nodes and the number of processes on each node, and they carry out the communication. Some of the communication could be local when you have more than one process in a node. And in these cases, the communication may not even go on the network. It will go in shared memory, and the node-to-node communication will go on the network. The next level of benchmark, this is the intermediate level, what I call a generic benchmark. One of them is HPL. It's a pretty old benchmark that involve factoring and solving systems of linear equation. It mainly include matrix multiplications, and some of the in the past, it used to be done by CPUs, but these days it's usually carried out by GPU. And HPC-G came to complement this benchmark that was used pretty often. HPC-G kind of extend the type of computation that are carried out. It's a conjugate gradient, which involve more irregular data access patterns, iteration. It's an iterative process, and it's more heavily used neighborhood collectives. HPCC is another type that is actually a set of 7 tests. HPL is one of them. Each of the 7 tests focus on the different aspects of the system. Not necessarily communication is just part of it. It could be memory, floating point, operation, and so on. There is a reference to these benchmarks at the bottom of each slide. The next level, and that's the kind of the highest level in the HPC, is the HPC applications themselves. There are a lot of different applications in HPC, and they can be, of course, used as a benchmark. You just run the application on your system using a certain MPI library and certain hardware and software and so on. One example of these is the weather forecasting application. In this case, a certain area is being simulated, and the way that this simulation is carried out is usually that the area is divided into sub areas. The blue that you see on the is there a pointer here? No. No. Okay. So the top left picture. This is where each rectangle is basically an area where an MPI process carry out the computation within this area. Everything that involves, for the particular application. And each of these processes in each iteration uses some boundary condition at the beginning. After it carry out the computation of the different dynamics that happen in this rectangle, it need to exchange the data with the neighbors to carry out to the next iteration of the simulation. So this benchmark, for example, can run on a system either with MPI only, but it can also run with a hybrid of MPI and OpenMP, where each MPI process will have several numbers of OpenMP thread underneath that will communicate among themselves. And then the MPI communication, which is represented with the white arrows, will happen only between MPI processes. Another type of applications that can be used for benchmarking is molecular dynamic. GROMACS is one of them. In this case, GROMACS, for example, was primarily designed for biochemical molecules like proteins and lipids and so on. Here as well, the system, as you can see on the picture on the right, is divided into sub cubes or sub pieces of the sub volumes where the simulation need to be carried out. And again, each process carry out the simulation, but again, we see that there is boundary condition. In this case, the boundary is an area between one volume and another. And in each iteration, there need to be some exchange of the parameters resulted in the current iteration, so they can be taken into account by the neighbors in the next iteration. LAMPS is another type of molecular dynamic application. On the picture here, we see some pictures taken from a video on their website, a pretty nice video that simulate blood flow. And here, similar kind of computations are done, like FFT, linear algebra, and so on. There are different types of benchmarks under different kind of tests under this benchmark. And the metrics are how many real nanoseconds are, or real life are being simulated per day of computation. And an interesting metric to take out of that is, of course, scaling, for example. So if you run the same test on one process, multiple processes on the same node, and then you move on to more nodes with more processes, and you could go on and on and on, and see the scaling of the performance when you increase the number of resources that used to carry out the computation across the network. We'll see a picture about this particular test later on in a later slide. Yeah. So there are more of these molecular dynamics, fluid dynamics, structural analysis like explosions and deformations. What's common to all of them is that they divide the area or the volume to sub-areas or sub-volumes. Sometime, like you can see on the car at the top there, the volumes may not necessarily be the same size, all of them, depending on the amount of data that need to be processed in, for example, here the areas are smaller near the body of the car, because there is more interesting stuff that's happening there that need to be simulated versus the far areas. And fluent is another type of fluid dynamics, acoustics, optics, and so on. They carry out some commonality in terms of the structure of how they run. And some of the takeaways here are that they all decompose the problem into some sub-volumes or areas. They must exchange some parameters between neighbors in each iteration, and iterations could be thousands or even tens of thousands of iterations. So this is a repeating pattern. You're doing the same thing over and over. Some of the interesting communication aspects of that is what is the size of this parameter exchange? Is it few bytes? Is it kilobytes? Is it megabytes? That's interesting depending on the application. What is the frequency and overlap of the exchanges? The type of communication that used in the exchange, what type of collective or point-to-point communication, and possibly alignment between the start of the communication by different processes on the whole cluster. So again, questions that relate to benchmarking, can these and other communication aspects be profiled per category, maybe like HPC and deep learning or storage? And then can benchmark mimic the relevant aspects of each category without carrying out the whole computation and the whole sequence of thousands or many or tens of thousands of iteration and pretty long time to run the whole application, and give a more focused information and feedback about communication itself, but as relevant to these categories. And I'll talk more about that in the last part of the presentation. Machine learning, here there are less known benchmark. Usually what one could use as a benchmark is just take an open source neural network model, install a framework for machine level neural network training like PyTorch or TensorFlow, and run the application, run the network. There are different in public domain different models, as well as the data set associated with them, like ResNet-50 for image classification, SSD for single shot detection. This is where the image is classified as well as positioned within the image. DLRM for recommendation system, natural language processing, and so on. One could take those and run them with whatever library that they like. These could take long. The training could take long. And it may require, in some cases, a GPU, because that's a realistic way of how most of these, at least the large one, are done. What we see here is an example from a profiling of an application where the different types of operations are marked, and more information could be extracted. So one could run this application, do some profiling, look at some other stuff, and try to extract from that what really happened in terms of communication. The measure of this kind of application, or the metric, is usually not directly related to communication. So if we look about things that were done so far that are a little bit more specific, there is a deep bench from Baidu. It's not directly aimed at testing communication, but it tried to do some basic operation that is carried out over and over again in a deep learning application, which is dense matrix multiply, convolutions, and of course the communication that relate to them. So this benchmark could be used to see how what the performance and how the system behave under this kind of operations. There is something called Param from Meta. It's not exactly a benchmark. It's really a repository for all kinds of benchmark and models that include standalone communication benchmark, which some of them are really like the micro benchmark, like Nickel, or the MPI micro benchmark. And some of them are aimed at more the linear algebra part of the system, the CUDA, neural network, MKL, and so on. The takeaway from here is again the focus. The focus here in this in the reporting of these benchmarks is on the accuracy of the training as well as the performance. It really tests the whole system, but also the framework itself, whether it's PyTorch or TensorFlow or another one, and the neural network. How good is the neural network itself doing in terms of the amount of computation it needs and how quickly it gets to accuracy. So it's kind of a more high-level metric. Communication specific is usually left for the micro benchmark in deep learning. And what would be desired here is similar to what mentioned for HPC. Could we profile the specific type of operation that are dominating this kind of applications? And can we build benchmark that will mimic that and will not have to run a full training session of something like that and just focus on the communication aspects? Okay, so we now get to another interesting aspect that does not relate directly to HPC or deep learning. It is common to anything, HPC, deep learning, storage, whatever is distributed on a network. And this is the effectiveness of congestion control. So application could be affected by the wellness of the congestion control in multiple ways. So few examples here are if the congestion control cause some unfairness between competing flows, when competing data streams are not getting the same amount of bandwidth share of the network, this could impact the final completion time of the application. Overreaction of congestion control to the point that the switch being underutilized. For example, in the case of congestion, if the congestion control react too much, all the streams that are congested may reduce rate to such a low level that they're not really using the available bandwidth altogether. So this could, of course, impact the performance of the application in the end, because they're not utilizing the resources, the communication resources, and not capturing available bandwidth after a congestion episode. So after a congestion episode, when some of the competing flows stop transmitting, there is suddenly available bandwidth. How quickly the remaining nodes that are still active capturing this bandwidth, this can have significant effect on the application. An important aspect is interference between application or between threads. If there are multiple type of communication traversing the network at the same time, is there interference between the two? Congestion at the receiver is oftentimes being neglected. The congestion in the receiver is a case where the congestion is not really in the network because there are multiple competing senders that try to reach a certain destination. It's really a congestion at the receiver itself. And this could happen when, for one example, if the CPUs on the receiving systems are currently busy and accessing the memory very intensively, then incoming packets that need to be placed into this memory need to compete with the local activity. And in such cases, you really have congestion not on the network, but congestion into the memory system. Is this even taken care of? Yes?
Just a quick question. So you mentioned that the bandwidth is underutilized for some periods of time. Do we have a notion for how much time the bandwidth is?
Well, that's something to be evaluated, right? So if just to give an example to clarify this point, if, for example, I have the simplest example, two nodes ascending to one other node, then each of them will take 50% of the bandwidth, roughly, if it's fair, right? But then let's say that then at some point that one of the nodes stop transmitting. So the other node is still transmitting at 50%, but now there is another 50% that it could capture. How long it take it to capture this 50%? Right? If you take it very long to capture, then you have a period of time where you're not taking advantage of the resources that are available to you. And if this happens over and over and over and over, this could accumulate and have a significant impact on the application.
So for us to capture this, we would need some feedback from the network, right? So the network provides some metrics to say that this is happening. So
yeah, I'll talk about it, and let's get back to this point when yeah. Yeah, and the last thing here is peak switch buffer usage. If we could measure, for example, what is the peak usage of buffer during congestion, we could understand things that could impact the performance in a sometimes severe way, like the possibility of drops in the network, or if priority flow control is enabled, but these peaks sustain for a long time, then we have a phenomenon called congestion spreading, where congestion and PFC coming from one switch could basically cause a reduction of the utilization across large parts of the system. So all of these effects are heavily dependent on congestion control algorithm. And GPCnet, for example, is a relevant benchmark that tests the overall impact of the network and congestion on performance of the different operation. And it does so by having a set of test transactions, certain MPI operation that are used as a test, and it runs those by themselves and measure the completion time of those, the latency. And then it uses another set of loading transactions that will cause congestion in the network, but those run on other set of nodes. And these two together, when they cross path in the network, they will influence, there will be interference. And what GPCnet does, it measures the test set performance under load. But the way that GPCnet is constructed is that one set is running on some of the nodes, the other set on other nodes, and then the only opportunity to cross paths is between switches in the network. So really the test is intended to test a pretty large scale network with multiple switches. What would be desired in this case is, for example, to have those different sets of transactions running on the same node, where they cross path even with a single switch, and not only that, but also on the NIC itself. They cross path on the NIC itself. So multiple types of operation goes through the same data path throughout the network from source to destination. And then we could have a richer set of metrics that give us a more granular indication of the impact of interference. But all the other points, GPCnet doesn't really test, at least not explicitly. So we really don't have a way today, any benchmark that really give us any answer to these particular explicit questions about congestion control.
very bad.
Yes.
Don't give a sense of when this is correct.
Right.
Saying that maybe some counter saying this is occurring, then the library can start to accordingly change its behavior.
Yeah, that's a good point. Yeah. So a few words about just the operational aspects of running multiple benchmark. When you do that, you may want to test different configurations of the network, put them in different modes, like, for example, use PFC or don't use PFC, use this congestion control algorithm or another, the number of nodes that are participate, the number of processes per node, which MPI libraries or which APIs you're going to use, or which options you want to give to the MPI libraries for example, for algorithms selections or others. This will require if you want to do a thorough work in this area, it require automation, and it will generate a significant amount of information. But this information is crucial to make some conclusions about the results. So automation in terms of configuring the network in a reliable and consistent way that avoid human errors versus doing things manually is very important. Configuring not just the systems and the NICs, but also the switches in the network. And then collecting statistics from the NICs and from the switches in the network. But then at the end, you need to parse all of that and present it in some human readable fashion that could give useful information. Here we see just two examples of for results. So for example, the test I mentioned earlier, lamps, you want to see the scaling of the test. So here the scaling is presented out of the data reported or the metrics reported from the lamps benchmark itself. You could compute the percentage of scaling across when you scale up the number of processes in the network. And in the case of war, for example, you could see how the main computation time of each iteration is going down when you increase the system. So this can give you a good indication of what happened. How much it buy me to add more resources? Does it scale linearly, close to linearly? Does it really buy me enough to justify more, putting more system in place to running this kind of application and so on? And when it comes to making sense of these things, then statistics like you see at the bottom here could give you a good and necessary information. For example, if I know that I'm running a collective in a ring fashion, I do not expect a lot of congestion to happen. So something that tells me what is the maximum egress queue level will indicate congestion in the switch. But if I see something that I do not expect here, it could give me some hint for why possibly the performance or some misbehavior that I'm seeing is occurring. Similarly, some statistics that relate to the NIC, and of course, the different types of transactions or exception event that happen on each of the nodes. So here we see some report of the number of read requests and responses, the number of write requests, and so on. So here we get to the last part of this presentation, and here I'm trying to promote and propose an additional set of benchmarks that could possibly close the gaps that we have today from communication perspective. So what might be the goals here? The goals here are to test particular patterns that are common to a category. So We could have a set of benchmark for each of the categories, for HPC, machine learning, another category, that represent really from the communication perspective, what is going on most often in this application. So, for example, the categories could be AI and deep learning, HPC. HPC may have more than one category, and storage application. And we want to be able to mix collective, and mixed collective is either run them concurrently or run them chained, one after the other, with a certain gaps or certain overlaps, in a way that represent the kind of operation, the kind of communication that happens in this application. And applications are not doing the same thing from this perspective. This will allow tuning of different parameters of the network and the equipment on the network per application. So the application could run in a better way. And it can also allow improvement in the algorithm selections by the MPI libraries. The focus of this potentially new benchmark would be the communication part without spending time in communication. And the main point here is that is actually twofold. It allows running the iteration much faster than you would if you want to get to these types of combination of transaction through the use of application. But it will also focus in terms of the metrics and the statistics and the visibility that you have. Even if you want to, for example, take some traces, you don't have to take traces on the network for 2 hours of application. You could do it over a few seconds where the actual communication that you're interested in are going on. So the focus here is really the main point. And it can cover, this kind of benchmark can cover aspects of congestion control explicitly. I listed some of them in the previous slide. It really, again, the focus on ability to get enough visibility into these things and do enough test scenarios that will be able to bring these out. This in particular can enable not just tuning, but also research and improvement in this area as applicable to, again, the different categories. So how might we as a community take on such an effort? This is, of course, could be carried out by one individual organization, but I believe that it will be most useful to get involvement and input from a broader set of experts that could be the equipment providers, the API developers, the MPI developers, and even the application developers in assisting in coming up with the right set of profiling and benchmarks to add. Here, I propose that the first step would be profiling of at least a certain type of applications in each category, and try to identify the type of operations that are performed, or the most frequent operations, how often they are carried out throughout the application. Interesting would be the distribution of either gaps or overlaps between the communication phases, in each category, the size of the communication group, the distribution and frequently of the message size, what amount of data is really being exchanged. This is in contrast to what happened, for example, in the micro benchmark, when you go ahead and test a collective from 1 byte to 8 megabyte. But what if the most interesting case for an application is 32 to 64 kilobyte? Well, you don't even care about everything else, and you want to see particularly this range as it applied to a particular application or particular set of applications. And then the next phase is, of course, to come up with a set of hopefully just a few benchmarks in each category. And the benchmark could include several communication operation, several collective operation that are either chained or concurrent. And the message sizes and the communication sizes that are most relevant. And one of the probably more complicated things is that the benchmark could repeat with either a fixed gap or overlap between the phases or with a random selection from a distribution of gaps and overlap. So it can give you a wide view of how the type of communication that are relevant to application are carried out, depending whether there is a specific gap between the phases or there is some distribution of the gap. And potentially allow for a selection of different MPI options, for example, within the benchmark. So for example, you may want to run this with forcing a particular type of algorithm for the operation that you use. And there is the other type of congestion control focused benchmark, and here I just go by putting a few examples to emphasize, and we're going to get back to you, the point you mentioned. So the most simple one is, for example, could be a loaded latency test where you create a congestion scenario by n number of nodes transmitting to one node, but at the same time, there is some small message size latency measuring thread that is running. And this gives you a very good indication of, okay, what happened to a victim flow during congestion. So you could modify the level of congestion by the number of nodes or the bandwidth that each one of them send, and see what is the impact on victim node. For example, another application that would have short messages traversing the network, how would it be impacted by the fact that there is congestion in the network? And there is clearly different congestion control that would do very different things in this kind of scenario. So this is a very low level, but very indicative of the behavior of the congestion control algorithm. This could be carried out by either by a perf test, combination of perf test operations, or by MPI by running two different sets, for example, all-to-all that will create congestion and maybe a point-to-point communication at the same time and see the interaction between them. Going to a little bit more involved, what happened in terms of the bandwidth capturing, the available bandwidth capturing after a congestion. So here, looking at the three phases really. The first phase is there is a set of n nodes that starting transmission. They compete. There is some share of bandwidth that each one of them get. And then in the second phase, another set of m nodes is starting to transmit. And in the third phase, these m nodes stop transmission. So one interesting thing to measure is what is the bandwidth of the n nodes in the third phase? After they compete with the m nodes and the m nodes went away, how quickly these other nodes uses this network. Again, if you look at it in one time, it may be a few milliseconds or a different number, and it may not seem very significant. But if these kind of things happen thousands of times during an application run, then it accumulates. Another thing that could be measured here is possibly the fairness during the second phase, where there is the first set that started first and the other set that joined later. How is the fairness between them? How quickly you reach fairness? Yes? between. Okay, you're talking about this particular one? So this is really, it's one test that composed of 3 phases, right? So let's say that we have 10 nodes that are transmitting towards a single destination. Obviously, they're competing for the resource, right? And there's going to be some bandwidth sharing between them. But overall, these 10 nodes will capture the 100% available bandwidth. And while this is going, there is another number of nodes, let's say another 10 nodes, that are also trying to get to the same destination. Now, each of these 20 nodes will have to reduce the rate, right, to have to go, and each one take 5% of the bandwidth rather than 10%. Now, at the third phase, the second 10 nodes stop transmission, and suddenly, after that happened, you have 50% of the bandwidth available that is not used right now. The first 10 nodes will have the opportunity to capture this bandwidth, to rise from 5% each to 10% each, right? So how quickly that happened have significant impact on the utilization of the resources. That's answer your questions? Yeah? And did we cover what you asked about? So really, if you measure the bandwidth on the third, if you're capable of recognizing, I mean, you're in control of when to start and stop these processes in the benchmark, and if you start measuring the bandwidth of the receiver in terms of just the amount of data that you receive, at this point, this gives you the direct indication of how much bandwidth is used. And you will see that it starts at 50% and start ramping up. But if you keep monitoring it, you will see how quickly it ramps up. Right? Yes. At the application level, you will see a delayed effect of that. Yes. It's true that if you want to see exactly what happened on the wire, you need some other mechanism. So the NICs do have statistics. I don't think that they will give you the statistic collection quickly enough. I mean, the sampling quickly enough. There are ways to maybe use counters on the switch or things like that, but it requires some investigation. But I think that it's pretty fair to assume that the application will give you a delayed version of the bandwidth, but it's okay because everything is going to be delayed. The 100% before the second set of nodes stop is delayed, as well as what happened after. So you will, I believe you're going to get a pretty good bandwidth picture of how the bandwidth ramps up. Yeah. Yes. Right. No, this is not. This doesn't cover that. Yeah. This is just one example. Yeah. Of course. Of course. Yeah, it's a very good question, right? Yeah. So these are just examples. I'm not trying to cover the whole thing, but what I'm giving this example just to get people to think about what this kind of benchmarks, how they can help us. But of course, there are more cases and there are more complex scenarios when you talk about congestion control. Yeah. GPC net, yes. I need to check. I gave a link there. You could look at the link. It's in the presentation, but I don't remember who, it's open. Yeah, it's open. I don't remember who wrote it. Okay. All right. Two more examples here again. These are just examples, but to get a good coverage, there are going to be other interesting cases to look for in this kind of benchmark is overreaction. Try to understand what is the bandwidth curve after there is a large incast. What happened in terms of the bandwidth. Large incast mean that there's a transient in terms of the behavior. And also switch memory usage. We could certainly use the latency measuring thread that we talked about earlier to give a very good estimate of how many kilobytes are sitting in the switch in the congested queue. This other thread will be able to measure that pretty well. And this gives you a good indication of within certain load and a certain type of congestion control algorithm, what is your risk of dropping packet or PFC spreading and so on by direct indication from the switch itself. So in summary, there is a good set of benchmarking that give a lot of metrics and useful information about different types of applications, especially in the HPC, in the deep learning. It involved mainly running the particular type of training that you are interested in, depending on the need. There are good micro-level benchmarks that give a very good focus on a particular type of operation, how it performed, how the devices that carry out the operation perform relative to other devices, or how one software library performs versus another. These are very good indications. There are some communication patterns and aspects that are not well covered, and it would be good if we could cover them. I think this will assist the community in tuning, getting better runtime with available equipment and software, as well as promote research and improvements in how we implement the different primitives and hardware of the communication, as well as congestion control. Any questions? Okay. All right, thank you.